turned on. Let's see, okay, I got a pretty boring background. Actually, it's a rather special background. It's a picture of the ground in Costa Rica. And right behind my head is these are all permeable pavers, and then there's a stormwater inlet in the middle of it. This is going by their, well, it'd be like our congressional building, except that unlike ours, they're used to having armed insurrection. But there were guards around it, so I was kind of sneaking these photos. Although in Costa Rica, if the guards get mad at you, the worst that's going to happen is you're going to get severely beaten. So in some ways, it's somewhat more civilized. Okay, welcome, Richard.
Yeah, thank you.
And everybody's here, so we shall start. So today, so I got the recorder turned on, yes. Today, when I go to the Blackboard link, I'm going to go to lesson 12 because lesson 11 is not it already. So I just went ahead and kind of quasi-prepped the next one. Lesson 11 would have been the hydrograph case in our homebrew. And I was having trouble getting it up and running, and I gave up, and we'll work on it later. So as grown-ups, we can do that, which is kind of cool. So I'm turning my screen sharing on now. I will suppress my email because that doesn't matter. I will make all the reminders go away. I have my Amazon web services ready to go in a second. I made sure I've got, looks like I have 72 minutes of compute time available, so that should last for today's lesson. In today's lesson, if you go here, you'll notice lesson 11 is missing. I'll get it put there as soon as I can. And today we're now making seemingly not much of a step, but actually a fairly big step in the way we are conceptualizing our systems. Well, that's awful small. So we're going to start into branch systems. So what we've talked about to date have been one-dimensional flow, and they've all been along a straight line, which is nice, but not necessarily reflective of the kind of conditions that we want to ask in our surface water modeling or in trying to do integrated hydrology and hydraulic modeling. So our next complication is to consider a branch system. That's why that was so small. So I could fit the picture on one page. So here's a diagram of an example we'll work through today, or at least get started today, of a branch system. And what's meant by branching is we have a main channel, which is indicated here by the words main channel, these large dashed lines. And then there's a tributary or a branch that's connected into it. And we could go more complicated than just this simple tributary branching, but this is a good place to start. So if you were to consider this as a computational exercise from cross-section number 6 down to cross-section number 1, that's no different than anything we have discussed to date. That's simply one-dimensional flow model. We could apply either a steady flow or unsteady solver to it. Assuming we have the cross-section geometry and a little more information, we're good to go. Or if we can consider from section 10 to section 1 and completely ignore this tributary, that's just a one-dimensional case. But when we introduce this side flow coming in, now we've complicated our lives somewhat, both in geometry and how we represent it to our computer. Because in this drawing from section number 14, arguably 14, 13, 12, 11, and even as far as to section 6, 5, 4, 3, 2, 1, that path right there can certainly be argued that that is a one-dimensional flow regime. But when we combine the two together, we have input at section 10 and input at section 14, output at section 1. We have a more complex problem. Duh. Not dimensionless unit hydrograph, but duh, almost dough, as Homer would say it. And the most, by far the more common way to handle this is we will treat from section 14 to 11 and as far as section 6 as 1D, and from section 10 to section 6 as 1D. We'll join the behavior at cross section 6 and then treat that as 1D from 6 on down to 1. Let's get up into readable size again. And so a branch system can be conceptualized as multiple one-dimensional spatial cases that have common junctions. In the example we'll do today, the common junction is junction 6. And at the common junctions, the usual approach is to require the conservation of stage. That is, the water surface can't have two different elevations at some single location, which is this essentially the same as stating that energy is unique at a cross section or a junction. That's the usual way of handling it. In some other instances, we might be concerned about the size of the junction, and then we would have to specify some sort of energy or momentum conservation within that junction element, which is how Heck-Rast takes the problem. For today, and in my broader general opinion, it's more sensible to let the junction stay infinitesimal and handle the resulting losses in the immediate downstream link. And where that actually really matters is if the sections are close enough together in real world that this angle matters. So imagine that this was a right angle entry, not as it's shown here, which is not exactly a right angle, but imagine it was a right angle entry. Think of what has to happen is water would enter that computational region, and then it's got to move downstream. For that to happen, the water, which has zero downstream velocity, has to accelerate towards the downstream. If these sections are far enough apart, we can more or less neglect worrying about that. But if they're relatively close together, the force to make that happen has to be addressed. And the tool to do that in that instance would be something like Heck-Rast. In SWM, we can approximate it by making some little artificial adjustments, which we will not do today, to handle that case. Because water doesn't accelerate instantaneously, so it can't immediately go from one direction to another without an external force. If this were a conventional fluid mechanics class, we'd make a big deal out of that and use it on an exam. But in this case, we're simply going to stipulate that at cross section 6, the water can only take on one elevation, or equivalent to saying that there's a single value of head at that location, and we'll let the energy balance take care of itself. So the error we're introducing, that there is conceptual error. We are neglecting the force required to steer the water. In small scale simulation, that's not realistic. at the scale that our tools are generally intended to be used for, it's mostly good enough. So the best way to proceed, so I have a note here that in future semesters we'll insert code. If we were doing our homebrew code, what we would see is that at one of our particular junction cells, at one of our I plus 1, I plus 2, we would have to bring in the information that's being communicated from the lateral input. And other than the actual scripting being a little bit mind-boggling, it's not all that hard. We have to require that at any computation step, the flow depths at that location, either the current or the projected one, are the same regardless of which one-dimensional channel that we are in. You have to take it on faith at this point that that's not all that hard to do once you set forward to do it. But instead, we'll go ahead and we'll treat this problem in SWM to get an idea of some of the issues with branched modeling. So here's our case. We have a main channel and a tributary, and there's a roadway going across it between sections 4 and 3. And this is actually illustrative of why you'd even want to ask questions like this of a model. And our question is going to be, is the bridge that goes here tall enough to be able to accommodate the combined flow of the tributary and the main channel? And generally speaking, we should have addressed that with hydrology ahead of time when we designed the bridge, but perhaps there's been some channel change. And so we're given a set of cross-section information that are shown here in this tabular / figure. So section 1, for example, measured from its left bank, distances of 0, 50, 200. I assume these are feet. You would think I know since I created the problem, but I don't. But I assume they're feet. And then we have elevations, 300, 280, 275, 265, and then back up to 300. So we have those for sections 1, 2, 3, 4, 5, 6, 7, 8, 9, section 10. And then in section 11, we have section 11, 12, 13, and 14 are also surveyed. And there's a little asterisk here that indicates that section 11 is measured between section 6 and 7. That's the meaning of the asterisk in the table. So section 11 connects somewhere between section 6 and 7, and judging from these spacing distances, section 6 is 960 feet upstream of section 1. Section 7 is 1,160 feet, and section 11 is shown here at 1,060 feet. So it connects between section 6 and section 7. Now, what we'll have to do in when we build a SWM model of this, because that's where I'm headed for today, is we'll either connect section 11 directly to section 7, or we'll just introduce an intermediate node, and we'll see how that goes. I have an older already built solution in case I completely fail at trying to build a SWM model of this. And we will have ultimately a homework assignment very similar to this setup, not identical. So we'll go through how to do it today. So any questions? So you get the idea. These tables are just cross sections, and if we were to plot them, they would look like cross sections. In fact, we'll do that in a little bit. So figure 2 is a table that contains the location of the cross sections relative to the diagram. So that explains those numbers next to the section name. And then the tables contain the X from the left bank and the Z from the left bank. So let's ask ourselves an obvious question. Is the lowest elevation in section 14 larger than the lowest elevation in section 1? Because that's kind of important. That means water's flowing downhill. So lowest one here is 271.2 feet. And we go to section 1, and its lowest is 265 feet. So indeed, section 14, the lowest elevation is higher than section 1 as anticipated. And we can check that for the other ones. Now that's not an absolute requirement. Water can flow uphill if it has enough momentum. But generally speaking, especially on these kind of distances, these are several hundred feet apart, we'd expect there to be a downhill trend moving from our upstreammost section to our downstreammost section. So a little bit more of the problem. So the road is cut into the surrounding grade so that the low chord of the bridge at the main channel is at elevation 290. The roadway surface is at elevation 295 feet. So the bridge deck plus the supporting beam is 5 feet tall. And we've given some steady flow conditions to consider. Let's go look at section 3, which is just downstream of the bridge. We may be able to answer this problem without modeling, but the lowest elevation is 266 feet. So there is 24 feet from that lowest elevation to the bottom of the bridge, to the low chord of the bridge. So certainly there is some distance for water to get through. So drought, we're going to have to do our modeling. And then this is a table of some steady flow conditions to consider. We'll initially just consider the first 3 rows. And then we'll maybe get on to how to do the parametric study, which is indicated by the area here where the cursor is circling around, possibly making you nauseous right now. So one of the cases would be the discharge at section 1 is 2,000 cubic feet per second. And that is comprised of 1,500 cubic feet per second coming in the main channel, 500 cubic feet per second coming in the tributary. And then we'll go up to 10-fold increase in both. And then a 5 times 30-fold increase in both. And just see, assess whether the channel can accommodate those flows. And so those are pretty extreme cases if you think of it. And then we can, if we want to, we can do a parametric study where we look at all the possible combinations. Let's see, there's 3 by 3, so it'd be 27 different combinations. We'll initially do steady flow. And then we will go ahead and re-ask the question, what if instead of it being a steady flow condition, we have hydrographs coming in? Does that make things better or worse? And I've suggested a few hydrographs here, starting at 2,000 cubic feet per second, peaking at just shy of 45,000 cubic feet per second. And there's a few other cases and this big long one. And what I'm trying to illustrate is sometimes the steady flow analysis isn't the whole story. And with a proper time varying hydrograph, we might discover that if we consider time, the discharge peaks don't always arrive at the same time, and our system may be more than adequate to convey the flow that we're interested in. And so we'll start to build a SWM model setup. And what we're trying to do is we want to determine if the current low chord can accommodate the steady design flows. So that's really straightforward, classic civil engineering kind of problem. And if the flow can't clear the low chord, then we'll treat the bridge as a culvert and see if the culvert's still big enough to convey flow without going over the top of the bridge, because that's generally a bad situation. Because even a Jeep in four-wheel drive doesn't float very well. And the Volkswagens that used to float, they haven't manufactured those in a long time. So if you get washed off the roadway surface, you have to practice swimming with an I, not SWMM. And that's not a good idea. I have a funny story about Volkswagens and floating. Many years ago, my wife and I were in Mexico, and I hired a car, and it was some old beater Volkswagen. So I think the guy that rented it to us, he worked at the hotel. I think it was his personal car, because he gave us a really good deal on it. And so we're driving down to a place called Punta Allen, which is kind of on the Mexico-Belize border in this Caribbean Sea. And we'd heard that they had good lobsters there. We had to get there before they turn off the generators, because they don't have their own ERCOT. They make electricity when they need it. And so we're driving down there, and there was lots of other adventure, going through an army checkpost, because they were looking for the bad guys importing drugs, and we were two gringos in a beat up Volkswagen with Mexican license plates. We didn't fit in, but after they decided that we were harmless, they let us go. Well, so we're driving back. We got the lobster. It was cool. It was a good trip. And on this, so this was not a highway. This was a dirt road going through essentially a jungle. And it started raining. And it turns out that this dirt road, nobody went to the trouble to actually make a dirt road. They just, we'll just declare the riverbed the road. It would have been nice to know that that was going to turn into a river. Fortunately, we had a Volkswagen that would float. And so we drove from high spot through these pools of water, and it would have enough momentum so the Volkswagen would float to the next high spot. And there was no choice. There was no pulling over and waiting for the water to go down. It was drive this thing until we die. And eventually got back to a proper highway that was paved. So when you go to exotic places, rent beat up old Volkswagens, because they float and they will get you home. So luckily we didn't make some international news as a couple of dumbass Americans drowned driving in a riverbed. Who'd have thunk it? So it's a funny story now, and it wasn't that terrifying at the time. We weren't going to die. I mean, but I had no idea what to do if we got to where the automobile wouldn't move anymore, because it's not exactly like there were telephones, cell phones, none of that shit existed. Okay, so that's why we want to do swim models of this situation, so that we don't have to drive a Volkswagen. So we're going to go through a swim model setup of this particular problem. And as we're going through it, keep in mind a couple of questions. And the whole point of doing that, which is, one of the questions is, how are we going to analyze the hydraulics? So as we're going along, we're going to make a series of assumptions. If we were doing this professionally, we would be writing those down as we go. So when we make a final report, we could explain to the reader how we got to the model and the decisions that we got to. The second thing to keep in mind is data preparation. I've done a little bit ahead of time in hopes that it will be easy when we try to do it in the cloud, but may have deluded myself. We'll find that out in a second. We'll probably get through the 3 steady close cases tonight, because if we can get one of them up and running, the other 2 are very subtle changes. And then I'll make a discussion on how we build inputs for the parametric study, where we wanted the flows to change. Then we'll try a dynamic flow case. And if it goes well, we'll try that tonight. If not, we'll do it next time. And then pretending that these are indeed the types of probabilistic flows that we would anticipate. We'll comment on the serviceability of the bridge with and without abutments, which is a large part of what civil engineering hydraulics is about. Not necessarily a bridge, but some infrastructure that could be impacted by the water in a channel or by the integrated hydrology and hydraulics. And let's see, and then speculate on what effect the bridge has on the channel system with and without abutments. If we can do 5, we can do 6. If we can do 6, we can do 5. So that's where we're headed for. All right, so I have gone ahead and I have a category called data files. And in that, there's a series of, oh, I forgot the README file. Okay, so the confluence one is a bitmap, which we can use in SWM. We can lay that into SWM and draw all of our stuff on top of it. So that makes it a little bit easier to actually construct the model. Got geometry data as a text file. Hopefully I have some way to get it. Yeah, I don't have the proper editor here, but I have a plan. Steady flows. These aren't that. We can manually enter the first 3 rows. And then an unsteady case 1 and unsteady case 2 are a couple of long hydrographs. So that's a minimal amount of data that we need. And then as an emergency, if I can't get it to work, I have an input file already built. And I'll probably revert that because looks like it has an unsteady hydrograph. So that's there in case we can't do it. There's the README file. Use the text files to make the SWM model BMP as a base map. I guess I don't need that now. Okay, so everyone understand where we're headed. So, okay, so now I'm switching to my Amazon one. I'll go ahead and connect using my remote desktop protocol. And it says connecting to my instance. Now we verified I have 70 minutes of compute time tonight. So that should last till the end of tonight's lesson. And do I want to restart that one? Sensei is not the correct. See if I can exit the tab. Oh, it decides it's got to run slow now, doesn't it? It knows there's an audience. So I'm not that mad. I'm spending more and more time on this Amazon stuff, so it doesn't surprise me that it hangs up a lot. Okay, that's an improvement. Minimize, resize. Yay. And if you're doing it on your own machine, you may not have this much fun. But we want to get to the web server. This should be lesson 12. Okay. First thing I'll do is I'm going to download the bitmap image. Want to save it into trying to find my SWM files because it'll be a lot easier to do it that way. Save it right there for the time being. Let's minimize that. We'll get our SWM program started and we'll try to get the base map loaded in. So we click on the SWMster. I'm glad I'm recording this because this will come in handy. Okay, we did get up to, I have in progress.inp. If you've had a chance, so we want a new, we've got the new folder. What we want to do is minimize that. EPA SWM project is where it's located, okay. Oh, I did a very poor job of laying everything out, didn't I? So the only thing missing is where I downloaded the file. Oh, I hate Windows because I don't use it enough, therefore I don't know how to use it. Well, worst case, I'll have to download it again. I'm looking for, so you guys can teach me something. How do I search for a file in Windows? I guess I do right here. .pmp. Why do you Windows people stand stuff that doesn't work? Just like Apple people stand stuff that breaks all the time. Scheiße and other German words. Let's try that again. Save target as EPA SWM problem. You have got to be kidding me.
You can check the examples folder. I think it's in there.
I didn't want it in there. I want it there. There we go. Okay, thank you very much. I'm glad somebody knows what I'm doing. So now, if you've not used SWM before, or if you don't remember from the last time you have, to put a background in, it comes under the view in the menu, and you choose the word backdrop, and then you get loaded. And so now we're going to load the backdrop, and at some point in time, it will give us a chance to search for it. We're going to load the backdrop named Confluence, choose open, press the OK button, and big deal, we've got a backdrop in there. And that gives us the opportunity to get started with any kind of modeling that we might want to do. If we were building it from scratch, we would probably put in nodes first. Well, we have to put in nodes first. And so I'll go ahead and do that. And now we are presented with an interesting thing to think of. In SWM, you apply geometry at a link. And a node is just where things connect. So what we have, we can either do what I'm going to do right there. We can make that node number 1. I'm putting the nodes between every section. And that way, between any node, a section defines the geometry. If it's roll your own code, you could choose to keep geometry at the node. Let's see, that's got to come across that link. And I probably have really butchered my numbering scheme. So I will arbitrarily make that my downstream end. And now we have this link 6, and we have to decide whether that's going to connect to that node or this node. I think it should connect to that one. So there's going to be that link 11. And there's no hard and fast rule for what I'm doing. This is a matter of analyst experience and understanding how the computer program works. I'm going to turn off the backdrop for a second. And there's just our node setup. So that's not very useful yet. And in between each of these nodes, we're going to have a link. And what we're going to do tonight actually constitutes a lot of work. So this is a case when you're doing your own that you're going to want to save things kind of early and often. So because I have no naming creativity, I'll call this example 5 hyphen confluence hyphen. And the last word, verbs, is the name of one of the authors of one of our reading materials from which this problem was taken. We'll do another confluence one on Buffalo Bayou in Houston. And I guess I could get self-righteous about it. We could call it Cleveland because it's a study that I participated in the early 1990s. Or we'll just call it Confluence Buffalo Bayou. Good, that's fine with me. Okay, so now we've created that, and we're going to have to manually, for all practical purposes, we're going to have to manually create each of these links in terms of geometry. So other than not wanting to have circular cross sections, call them irregular, and I'll just call it placeholder. So I'm making stuff up just so you can see how we'll handle. So there's manual data entry for a regular cross section, and we can take a look at it. And it's not a very interesting one as of yet. We also have the ability to provide left and right bank stationing. So we could set the left bank starts at, do this right, 101. Right bank starts at 201. Oh, it didn't behave me. You notice the color change. So anything from this position to that position is the left bank, and anything from this position to that position is the right bank, and anything in blue, it represents the channel section. And in this particular cross section, it's extremely uninteresting. I will give the name of this transect the name placeholder, which isn't a very interesting name, but I think you will see why in a second. And we're going to have to manually adjust how far apart everything is. So the only advantage of preconditioning these is irregular, is it's going to be one less step. Well, basically, we'll have the advantage of being able to cut and paste the station information into it, change the transect name, and save it. It saves one step of having to go from a circular to an irregular. Okay, I tend to build my nodes from the downstream upstream, and then build my links from upstream to downstream, which is probably really stupid, but it works for me. But actually, I'm not going to do that. I will try to adhere to my numbering scheme. So that's going to be link number 1, which will be the information will be completely contained in cross section 1. And let's now see, let me go ahead and save that. Let's now see if we can download the file for cross section 1 and manipulate it without having to do manual data entry. So I will minimize that. I will go back to this guy thing here. Right click, save target as. So let's see what options we have to open it with. I have Notepad and WordPad. I thought I'd installed LibreOffice. Let's see what happens in Notepad. I want to just get those 2 columns, so there's no convenient way just yet. I have an idea. Oh, you piece of crap. Can't handle 2 open at once? Sorry for practicing my profanity. Let me just copy that and what? Copy. Paste. Oh, I was crap. It'd be handy to have a spreadsheet program. So we could do that in our, I think we can probably do that in Jupyter Hub. Let's go ahead and try that. So I need a working Jupyter Hub. So mine happens to be this one. Yes, I know I'll be redirected. That's why I went there. You guys will have to do it on your local computer. If you're using the same setup that I'm doing, we need to get into the right deal. Okay, so here's our data files right now, and I want to open those as a that is no advantage. Especially if I click on the wrong file, geometry. It's a whole lot easier when you have a working spreadsheet, you know that? Okay. Bear with me while I get a working spreadsheet. I hope there's enough resources to do this and still have some compute time left. Installation instructions. Oh wait, I'm in Windows, aren't I? That was a mistake. I hope this is fast. No, but I prefer a stable one. Is it here? Oh, there it is. This is the cool part of cloud computing. So this takes an eternity when I do it at home, and if it doesn't break everything. So I didn't check to make sure that I have a virtual machine that has enough capability. But we'll find out the engineering way, which is just try it, and if it doesn't work, we're yeah, it's really quick. We'll have a spreadsheet in a minute. you will be able to legitimately claim that you have done cloud computing this semester. And then when your future employer asks you about it, you say it's the worst thing that we could possibly do because it never works when there's a client watching. And if we're trying to be state of the art, we want to make sure that everything works ahead of time. Actually, that's amazing progress so far. So this particular Windows virtual machine is 512 megabytes of RAM on the Amazon server somewhere, which is minuscule. And the smallest ones that you buy at Best Buy are at least 4 gigabytes. It usually needs 8. So if this actually, after the install, actually runs reasonably stable, that's kind of a miracle. And the reason I'd even try doing that on a cloud computer, so one thing you have in a cloud computer is essentially infinite swap space. So you don't need to pay for any more RAM than normal, or then you don't need to pay for RAM as much as you do on a personal computer. Oh, this could be, well, here we're going to attempt a remote reboot. So at some point oh, cool, it's going to do it in the virtual space. I thought I was going to disconnect. That's kind of cool. Now we're just staring at a blue screen that says wait. That's what I was hoping for. So that indeed did a correct reboot. So I will have to reconnect. Let's take a look at how much, yeah, that install used up a fair amount of CPU minutes. Oh, actually, that's not bad. We went from 72 to 68, so 4 minutes of clock time. That's not bad at all. Again, the reason those minutes don't add up to our real perceived time is you're only paying for the actual clock cycles it needed. And there was a lot of time when I was talking, attempting to entertain you all, that the computer was doing nothing. I mean, after it attempted to monetize every action and couldn't. Let's see if we're back up yet. This is where I wish I had Tom Petty and the Heartbreakers singing "The Waiting is the Hardest Part." But I found out when you do videos that if you do something like that, that's copyrighted material and they can detect it. And a lot of times I can post the video and then send you guys links and you can't look at them. Because everybody's trying to get money, ourselves included. Let's see if that thing is even running. It says it's running. $20.45. That may not have been such a good idea. Ooh. 2050, that was 5 minutes ago, so it has no data for right now. It should have been long enough for it to reboot, so well, I can't reconnect if it's not going to let me anyway. I'm going to go ahead and stop it, and I'll show you how we would normally process this if you have it on your local machine, giving it a chance to restart. So for any of you that are, I imagine most of you are probably doing it on your home computer, but if anyone else is following along on the on a cloud virtual machine like I am. So the stopping and starting is kind of the violent way to regain control. It always works, but it takes a fair amount of perceived time. Okay, so now that it's stopped, I'll restart it, and we should be able to regain control of the computer momentarily. Hopefully the public IP doesn't change, because that's going to screw up everything. And the Windows restarts are taken, to me, they take a whole lot longer than the Linux restarts. And supposedly they have a Macintosh operating system running on Amazon Web Services, but I don't quite get the point of why you would do that. Run a crummy operating system on a network limited thing. So this is my best chance to get a reconnection. If I can't reconnect now, I got the spinning ball. Please wait. The good thing airplanes don't fly with software driving the airplane. That would just be a disaster. I have my niece's husband flies airplanes for a living. And once we were talking, and he flies Airbuses. So those are basically Windows operating systems attached to an airplane. He says, well, you ever been flying, when it feels like the plane's just kind of wallowing around in the air, completely out of control? I go, yeah, I've been that. He says, yeah, that's because we're rebooting all the computers. It's like, oh, that's good to know. He says, no, don't worry too much. As long as we have both engines turning, we can steer the plane using thrust vectoring, and we have a trim tab that's a mechanical trim tab that'll let us go up and down. But when the computers fail, that's the only control they have, is a little bit of steering by thrust vectoring. And there's my LibreOffice, which, oh, that wasn't what I wanted to click. Dang it. Okay, let's try to get window. Okay, let me get SWM up and running again. You see why I decided to save the input file before I started doing these shenanigans? We'll be using calc in a minute, but okay, SWM is running. Let's go ahead and open. Hopefully example 5 wasn't stuck in the buffer. It wasn't. Choose open. Okay, and we have our conduit 1 right here. I'm going to minimize it. Oh, I have a bunch of instances open. A lot. Okay, so there's the one instance that we want. And So I think we've already downloaded geometry.dat. So let me minimize that. Now I'm going to want to go here and open that geometry.dat file. Open with LibreOffice, and it should recognize that as a spreadsheet type file. No, it does it in the writer. Close that. File. New spreadsheet. Okay, so I want to open. Oh, I know what I want to do. I just want to cut and paste if I have to. Okay, tab, delimited, separated, tab, comma, semicolon, choose the OK. Yay! All right, now we can cut and paste into SWM. Notice how much money we actually paid for the software. $12 a month for the Amazon Web Services is all I'm paying. Software was all free. So I'm going to try to copy X and Z. So it allowed me to copy. I'll go to SWM, open up my conduit. It made it a circular one anyway, piece of junk. Give it a name. Oh, sweet. So we got our section one, not a very interesting cross section. So here's the channel part, and this other stuff has got to be the overbank part. So our overbank starts at 200 and whatever the 260 is. So overbank, that's overbank. So 210 is our channel. And 260. We'll deal with the roughness later. Let's not quite. We'll go to the next one. So it takes a little bit of fussing the first time through, or the 10th time through in my case, because I don't do it every day. So that's what we're trying to create. And then later on, we can actually provide a different resistance term for this portion, that portion, and the channel portion. Let's take the whole word. We'll just call it S1 for section 1. And we could put a description if we wanted to. We'll press the okie dokie button. And it took care of our max depth for us. To get the length that the channel would have to be, close that. We save that, shrink that. So section 1 is going from 0 to 200. So essentially it's 200 feet long. So we would put that at 200. And I actually forget what Manning's N for this problem is. So it's going to be 0.035. Because that's always a good Manning's N when you have no idea and you know it's a natural channel. Okay, so we've done one of the cross sections. Let me unload the backdrop. Actually, I'm really quite pleased that we're running SWM and LibreOffice on what would operationally be a very crippled computer, and it's working. So we've done that one cross section. Now we'll just go ahead and do the next one. There's cross section number 2, and now we want to go ahead and parameterize it. Tell it that it's irregular. We'll call this one S2. We'll have to put some information in for it, and we will get that information. Oh, you piece of junk. Hopefully it'll let me put in an empty section. It will. So section 2, copy that. Bring up our SWM model. Paste. I'm going to guess that our left bank starts at 190. Our right bank starts at 256.5. Take a look to be sure I got it right. Choose the okie dokie. 2 sections. All right, let me download a completed SWM model, because that's the basis of the hard work, is one section at a time and setting up the connectivity. So let me shrink that. I'm going to close my exit LibreOffice. How do I close the one I'm on? I think it's that one. That was me growling. We'll return to our, I'll just grab a working input file, right click, save link as, and it has a different name, so we'll just leave it right there. So I'll leave this one partially built, but I want you to see where we're headed. Okay, so here's what it looks like all built. I'm going to turn off the backdrop. And there's our model. Let's see. Okay, so our river station 1 to the outlet is what we had as section 1. And section 2 is river station 2 to river station 1. River station 3 to 2, 4 to 3, 5 to 4, 6 to 5. So this naming scheme is something that the analyst or I came up with a while ago. 7 to 6, 8 to 7, 9 to 8, 10 to 9, main channel to 10, and then working on the tributary 11 to 6, 12 to 11, 13 to 12, 14 to 13, tributary to 14. So at this point right here is important to consider. So this one is taking junction 12 and connecting it to junction 7. But the naming convention is taking cross sections 11 to 6. Fairly similar to what's in the written description. Let's look at the upstream end. It has an inflow, and it's doing a time series, but let's go ahead and save this as a different name so that I can go ahead and break things. File, save as. And go ahead and clobber the existing one. Yeah. Sweet. Okay. Ta-ta for now. We'll go ahead and break that, and we can put a baseline flow, say 10. Choose OK. We'll go on this one. We'll go ahead and break that time series. We'll put a baseline flow of 10. Choose OK. And at the downstream end, looks like we did a free outfall. So that's going to allow the water depth to pass through critical depth downstream of our model. So that's one option. We could do a fixed outfall, or we could do normal. Let's switch it to normal and see what happens, since I'm breaking everything as we see fit. And let's just pick one of these junctions. You'll notice the invert elevation of the junction is set here so that it preserves the correct bottom elevations as indicated by the channel cross sections. So probably the easiest way to see that is, let's go ahead and draw a profile. We'll draw it from here to the end. So keep in mind that there's a tributary coming in here somewhere. And so here's our main channel profile. A couple of fairly long runs in terms of overall distance, and then all the interesting behavior happening in the vicinity of our bridge, which is right here is our bridge between sections 3 and 4. And we have a tributary coming in right there. Sadly, we can't draw both profiles at once in this particular current version of SWM. So I don't have to do that again. I'm going to leave that one up, but I can minimize its size. We can also make a profile from the tributary. We'll start there, and we'll just go to the junction, although we could conceivably go all the way to the outlet. So there's the tributary coming into the junction. It looks like we have, I have some vertical issues right here, but I will ignore them for the time being. Let's go see how the simulation is set up to run. If you remember back in options, we have flow routing, dynamic wave, although I've just changed this from a dynamic to a steady flow model by changing those input conditions. It's going to run for 13. Looks like it's set up to run for a 4-day simulation. I'll leave that be, because for steady flow, it should be able to get through that really fast. And I wanted to report everything every 15 simulation minutes. Okay, we're set to go. So run that. Oh, that's amazingly fast. Let's go look at our profiles. So the long profile, not very much water in it, but that's because we gave it a flow of 10 cubic feet per second. If we look at the tributary, which I think is this one, the tributary, same thing, not very much interesting going on. Let's go now back and look at our original problem statement. Original problem statement was 1500 and 500. So we can go ahead and change those values in our simulation. So this was 1500. And this one is 500. I'm gonna play with these so you can do some shenanigans here for what we're trying to do. You can set them so they can kind of be viewed at the same time. On a on your own computer, if you have enough screen real estate, so I'm actually limited because of the desktop manager that Amazon gives me on the light sail instance on how much screen real estate I have. And actually, that's not really a complaint. The fact I could be doing this on my phone if I wanted to is kind of cool. I don't recommend that you do this kind of stuff on a phone unless you're showing off to one of those client things. Because if you can do it and nobody else in the room can, you have just sold your business to the client in a big way. So I've changed the inputs. Let me go ahead and rerun the simulation. Hopefully everything stays in place. So the first few time steps of the simulation is just everything coming to equilibrium. So we won't worry very much about them, except that it looks like our system is in plenty of equilibrium. So going on the conjecture that this is actually correct, let's look at the water surface elevation at nodes 3 and nodes 3 and 4, because our bridge is between the two. And our important question is it lower than 290 feet of elevation? Actually, I don't even have to interrogate the database. 290 feet is right about where the arrow of the cursor is, and the biggest water elevation is quite a bit below that. So that first pair of flow conditions is well within the capability of the channel to manage it. Let's go ahead and go to the next set of flow conditions, which I believe was a 10-fold increase. So I can do 10-fold increases in my head. You put a 0 on the tail end of it. The 30-fold increase, I won't be able to do that in my head, although 3 times 5 is 15. At least it used to be. So now we're going to the next flow condition. I'm kind of hoping I set the geometry of the model so that there is some impact. And so this up and down stuff is discomforting, but I'm not sure if that is as much a consequence of the plotting as anything else. Between sections 3 and 4, we're still below 290, although we're approaching it. And if we go to the next set of inputs, which was 15 times 3, that's going to be 45 of them. Oh, I'm pretty sure that's going to clobber everything. And we're now above the bottom chord of the bridge. And you can probably see it right up here, but to really study the bridge, let's just produce our bridge is, actually I don't remember where the bridge is. Our bridge is in this conduit. So let's do a profile from there to just downstream of the bridge, which is junction 4. So we'll run a profile from current 1 to junction 4. It should be able to manage the path. It's only 2 links. And our magic number is 290. So according to our simulation, we're still below elevation 290 on our steady flow cases. So returning to our original problem, was, can the bridge low chord accommodate the steady design flows? The answer in this instance is yes, at least as where the bridge spans the channel. We haven't included abutments, and we'll go ahead and we can make that change. We got a couple minutes left and we'll be done for this evening, and we'll pick up this problem next time, and I will get a copy of the input file that I just saved in a few seconds up to the server so you all can access it yourself, unless you really want the pleasant task of running in one cross section at a time. There was a time when I would have been kind of making you do that, but there's no benefit for you to manually enter cross sections more than one cross section. You've seen how to do it, and if you have a spreadsheet, it makes the cutting and pasting a little easier. Okay, so let's answer this question. Bridge low chord can accommodate the steady design flow? At least as modeled, the answer would be yes. Let's go ahead and instead, let's look at this conduit where the bridge is. So that's this one. Let's look at what it looks like. If we look at the conduit, elevation 290 is up here. So as drawn, our bridge goes from station 125 to roughly 325. So that's a 200-foot long bridge. That is not normally how you would build it. See if I can actually, yeah, I have to, normally the way bridges are built is we take this section here and we fill it with rocks and floor sweepings and leftover shopping carts and refrigerators, and then spritz a little bit of concrete on top of it and call that good. And then the bridge, the actual span only has to be 50 or 60 feet. And all kidding aside, that's a logical way to build things because the channel valley doesn't have these high flows all the time. Our channel part has to be cleared. And so what we're going to do is I'm going to introduce a few additional points here. It's a pity we can't do it graphically. I'm going to have to do it from memory. So I want to keep this slope. So looks like position 125, 290. I think I can Copy that. Paste, good, that worked right. 125, 290, that's where we're going to start our bridge abutment, and we're going to take it all the way to where the channel stations begin. And then 290, we could take a look at it. Oh, so I've got to make my left abutment a little bit longer. So that might be more like how we would build a bridge. So all this area in here is fill material that we got from somewhere else, Home Depot, or actually Public Works Depot. It's just like Home Depot, only more expensive and less reliable. Kidding. And now we'll go ahead and put an abutment here. Maybe go about 10 feet and then bring those back up to 290. Oops, I got a little bit ambitious with that abutment, didn't I? God, I don't think I have an undo, darn it. So what was that one? That had to be 276, 266 and a half, 266. And I need to insert so this is just software manipulation at this point. There we go. So now our bridge is right here, and it's only about, let's see, there's 10, 60, still a little bit long, 70, 80 foot long bridge. And that's getting to be a little bit more realistic. Any longer, we have to start putting pilings in the stream, in the stream. Okay, so now we've modified this particular cross section to better reflect what a bridge might really look like. And you don't have to do it willy-nilly like I just did there. You would actually have correct information in a real simulation case. And now I have a feeling the bridge is going to have a substantial impact in the flow, or vice versa. Yay. So we have a lot of influence. Did I change the wrong section? I bet I did. That was stupid. So what's going on there? Why is it all wiggly like that? Because the flow is having to be squished through that smaller area. And in this particular instance, the wave action bouncing back and forth in the numerical wave is problematic. One thing we can attempt is we'll go ahead and try to dampen some of the inertia terms. And so what that'll do is it should make the solution a little smoother. And we don't have to run this one all the way to the end. I think 1 day should be plenty. And then I will stop, save the file, and we'll call it a night because I just looked at the time and I'm already 1 minute into your dinner time. If we dampen things, we're still having instability issues. And that's fairly common with using an unsteady flow model to replicate a steady flow situation. We will resolve that next class meeting. I'm going to close all these. Leave the study area map, save the file, exit SWM, choose DA, and let's see if I'll do that after I hang up on the phone. I'll put that input file back into the shared space. I could do it. I'll be doing it from here, but there's no point. There's no need for you to watch me do it. You've already seen me manipulate files that I didn't intend to already. We'll pick up this example next time. What we're going to do next time is we will actually put the dynamic routing in. All right. That's all I have for tonight. Thanks for your attention, and sorry for a little bit of the having to get the web instance to work correctly, but that happens from time to time. And I will see you on Wednesday, and have a great evening. And how's your how's the projects that you're working on coming so far? Making progress? Even started them? Don't care because they're not due till next week.
Mm,
I
okay.
mean, I was gonna try and start it this weekend, but it's kind of crazy, so I haven't gotten
Right.
to it just yet.
Okay, well, take a look at them when you can, because it just gets harder as time goes by. All right, well, I will see you on Wednesday. Have a good evening, everybody.
Have a good night.
Good night.
Yeah.
Good
Bye-bye.
night.